Welcome to tutorial 18 in the Practical RF Design tutorial series. I am Dr. Prakash Sangaran from InnoWave. In this tutorial series, we will learn the complete design and optimization guide for a 4G and 5G antenna using Keysight ADS. In the part 1 of this tutorial, which is part 15 of the Practical RF Design with Keysight ADS tutorial series, we learned antenna introduction, antenna selection, and PIFA antenna design. In part 2, which is part 16 of Practical RF Design with Keysight ADS tutorial series, we learned part 1 of the antenna optimization. In part 3, which is part 17 of the Practical RF Design with Keysight ADS tutorial series, we learned part 2 of the antenna optimization. This is a continuation of part 17, so if you haven't watched the previous parts, please watch it first. In part 18, we will learn about the PIFA antenna EM simulation and its results and analysis. In part 17 of this tutorial series, we have started the optimization. As you can see, the optimization is ongoing. Since I started the optimization last night, the goals have almost been met and the error rate is low. Due to this, I will cancel this optimization so we can look at the results. This is the optimization results. Since we optimized the antenna for a good S11, I have plotted the S11 in the data display server. Our frequency band of interest is 746 MHz to 960 MHz and 1.71 GHz to 2.69 GHz. As you can see, the markers are not set at the correct frequencies, so I will move them manually. This can be done by selecting the markers and pressing up or down keys on your keyboard. The antenna exhibits less than -6 dB return loss across the frequency band of 746 MHz to 960 MHz and 1.71 GHz to 2.69 GHz, which indicates the antenna meet the specifications. I believe further optimization and tweaking will improve these results. In order to simulate the far field parameters such as gain, directivity and radiation efficiency, we need to do an EM simulation with the saved fields option enabled. To do an EM simulation, we need to generate a layout from the schematic. We are generating a layout from the schematic because it has the optimized antenna parameters. Generate the equivalent layout to the optimized schematic by clicking Layout, Generate or Update Layout. When you click Apply, the layout will appear. The layout needs to be flattened so the pins can be placed within. Pins are needed to create a port for the simulation. To flatten the layout, right-click on the layout, go to Component and select Flatten. A pop-up menu will appear with options. Flatten all level of hierarchy to shapes is the right option for this design, so we click Apply and OK. Since I already have a flattened layout with the pins placed, I will delete the newly flattened layout. Let's take a closer look at the pins placed on the layout. You can place the pins by clicking Insert Pin. Here is the port setup in the port editor. The next thing to do is to set up the EM setup. The EM simulator is set to FEM. The frequency range and frequency points are set to our preferred frequencies. The most important thing is that under the output plan, we need to enable save fields by selecting all the generated frequencies or user-defined frequencies. I choose all the generated frequencies. The rest of the settings can be default as for now. All the settings have been set before, and that's why you are seeing a fully done EM setup. The simulation is executed by clicking Simulate, which is located in the EM setup under the model. Since we are doing EM simulation for 6 frequency points together with the frequency range and also have Save Fields option enabled for all the frequencies, This process will take time. Due to this, I will fast forward this process. Here is the return loss results again. This time, this is from the layout EM simulation. We also got return loss results after optimization. As you can guess, both are similar. The return loss meets the specification for the frequency band of 746 MHz to 960 MHz and 1.71 GHz to 2.69 GHz. Next, let's look at the far field parameters. To get them, click on Far Field button as demonstrated. The far field simulation is in progress now. Finally, the far field simulation is completed and the 3D radiation pattern and antenna 3D view are launched with the far field results. In the solution setup, you can choose the frequency of interest. After that, click Far Field and Antenna Parameters to display all the far field parameters such as gain, directivity and radiation efficiency for that particular frequency. At 746 MHz, the directivity, gain and radiation efficiency are 2.2 dBi, 1.9 dBi and 94% respectively. After that, let's move on to the 960 MHz frequency point. The directivity, gain and efficiency are 2.5 dBi, 2.3 dBi and 95% respectively. The next frequency point is 1.71 GHz. As I change the frequency, you will notice that the far field radiation also changes. The directivity, gain and efficiency are 5.3 dBi, 5.1 dBi and 94% respectively for 1.71 GHz. At 1.99 GHz, the directivity, gain and radiation efficiency are 6 dBi, 5.8 dBi and 95% respectively. At 2.11 GHz, the directivity, gain and radiation efficiency are 6.2 dBi, 6 dBi and 94% respectively. At 2.4 GHz, the directivity, gain and radiation efficiency are 6.4 dBi, 6.1 dBi and 94% respectively. Finally, at 2.69 GHz, the directivity, gain and radiation efficiency are 7.71 dBi, 7.2 dBi and 90% respectively. Last but not the least, you can also rotate the antenna's 3D view and radiation pattern. This is the end of the design and optimization of a 4G and 5G antenna tutorial series. I hope you will like this. If you do, please click the like button and comment below. See you in my next video with another interesting problem. Thank you for watching tutorial 18. For inquiries, please email pragash@innovave.co or visit www.innovave.co.